Okay. Tower of Hanoi, I'm not going to go over this one in class. It's fairly straightforward. If you read the description in the book, the description is correct. The code is wrong. It turns out that I was moving around the definition of the um, needle that you're moving from and to, and I changed the order of the parameters in my method, but I forgot to change the order of the parameters in the call to the method. Like, oops. So what you see in the output in the book is not correct. I'm using a local copy and it's correct. I'm going to talk to the person who's in charge and ask him to rebuild the book and upload it again so that it'll be correct for everybody. So just be warned that if you try the code, you're going to get the wrong answer. There'd be an interesting little challenge to fix it and see if you can get it to work correctly with the method the way I have it. So let's go on to this one, the exploring a maze. And this is the thing that just bugs me about teaching this chapter is that the recursion itself, if you look at this page, the recursion is not that much of the problem. That's the maybe 10% of it. The rest of the program, the problem is setting everything up, getting your data read in, and making sure that all the drawing happens correctly. So that's 90% of it. The recursion is next to nothing. And, but here's the idea, is that we're in the middle of a maze somewhere, and we need to find the exit. And there's a nice recursive method that will help us with this. Now, it's not going to be the optimal method. So it's not going to be the shortest possible path, but it's very elegant and it's a nice description of how to do it. So what we're going to do is we're going to divide the maze up into squares, and it's either open, like this one here. In fact, let's go here. This one here is open at the north, and it's open, well, it's open on all four sides. This one here is open to the west and to the north, but not to the east and south. Yeah. So that's the idea, that we're going to have individual squares and we're going to move from square to square. And in fact, let's go here. So what we're going to do is, if we're in the middle of the maze and we want to find an exit, we're going to search from we're going to have a starting point and we're going to search from there to find the exit. So first thing we're going to do is we're going to go north one square. And then if we can go north, we're going to say, okay, fine. Now let's start searching for an exit starting at that square that we just moved to. There's our recursion right there. So search from says, from where I am, try and find an exit. And it'll come back with either true or false. Let's say we can't go north. If we can't go north, then we'll try going south. And if we can go south, great. Then we're going to say, now I'm at a new place. Now let me try and find an exit from where I am. Again, calling search from recursively. If we can't go south, we'll try going to the west and recursively apply. If we can't go north, south, and west, then we'll try and go to the east. And if none of those directions work, then there's no way to get out of the maze. So that's what it is. And let me give an example of what's happening. Now, that's a good plan right there. But there are some things that we're going to have to keep track of in order for this to work. So let's say I'm here in the middle of the maze and I want to find my way out. I start by moving north. Okay, fine. Now, starting from here, what do? I'm going to move north. Well, that doesn't work, so I'm going to move south. Okay, great. Now I'm back where I started. Well, that's not going to be of any help. And you see the problem here. So what we need to do is, I can't go south on this. Okay, let's go here. When I'm here, I can't move north, but I can't move south either because I've already visited that place. I've already tried from there. So I never want to back up to where I used to be. So we need to keep track of the squares that have been visited. Once we do that, then things change a little bit. Again, starting from here, we're going to move north. We can do that. There's an opening. And we're going to remember where we were so that we visited this square already. This place has already been visited. Now we try to move north. That doesn't work, and we can't move south either because that would return us to where we were, and we'd be in an infinite loop. And since this is already visited, now we can move east, and we keep track of this to make sure that we don't go back up over it. Then from here, we could move north. We couldn't move north again. We couldn't move south. We could move east. And then eventually we would hit a dead end, and then we would have to backtrack recursively. The recursion would unwind itself, and we'd get back to where we are. And then we could continue from here to the west, and eventually we'd get out here at this exit. Okay, so that's the idea of this. Okay, now what are our base cases? There are 4 base cases in this instance. Normally there's only one base case, but there are 4 conditions which will cause us to stop recursion. First one is we've run into a wall. So let's go. So for example, when we tried to move west, we can't go, searching from there fails. If we try to move west from this place, because we've hit a wall. If we found a square that's already been explored, we can't continue exploring, otherwise we get into a loop. That's the one we just figured out. We can also stop our recursion if we found an outside edge that's not occupied by a wall. So the moment we get beyond the boundaries of the maze, we're out. We found an exit. And the other problem is we have to stop recursion if we've explored a square unsuccessfully in all 4 directions. Then guaranteed we can't use that as our path to get out. So let's look at the program on this. Oh. Sorry, I've got a whole bunch of other stuff here. Yeah, there we go. And what we're going to do is we're going to have an array. Okay, back up here. First of all, how do we represent the maze? And the way we're going to represent it is as a text file. So the walls will be plus signs. The empty spaces will be empty squares in the maze, and this S will be our starting position. And you'll notice that there's no wall here at the edge, so this is going to be our exit point. Yeah, this is not a typical maze where you have both an entry and an exit. This is going to be just one exit only. Rewriting it so that it would work with an entry point and exit point is a little bit trickier, so that's probably why they didn't do it. So now the question is, how are we going to represent this? We're going to do it with strings. So we can have an array of strings. And I'm going to get back to this in a moment. So each of these lines, we're going to split into an array of strings, and each element in that array is going to have a letter telling us whether it's a start, whether it's a wall. A dot will mean we've already tried it. A dash will mean it's a dead end, and an O means this is part of a path that will get us to the exit. So by changing these strings, we're going to be able to figure out what the status of the maze is. And we're going to have a turtle so we can see this thing actually drawing it as it goes along. We need to know how many rows there are, how many columns, and we also need to know the starting row and column. Now, here comes the problem is we have this is a fairly small maze, but we don't know how many lines it's going to be. There could be 100 rows and 50 columns, right? So we need an array list for each row. We could get around it. We could use an array by reading the whole file, figuring out how many lines there are, and then allocating an array that's exactly that big. And then figuring out how long each line is, so the subarray, so we could do it with the 2-dimensional array. But that would require us to read the file twice. That's actually not too bad. Okay, I wouldn't mind doing that. Let's check something here. But for right now, I came up with and this is ugly. Actually, this is really ugly. I'm going to have an array of string. My plan, here's my plan. I need an array list for each row because I don't know how many there are going to be. And remember, arrays have a fixed size, but array lists don't. I can use the split method. And what the split method does, do you remember that? Let's go back to JShell. And let's say I have something like string s equals plus. And then I can say s dot split. Oh. And I give it the null string, empty string, and that'll split it into each individual character. So I can get an array that's the correct length that I want. So rather than having an array list of array list, which I would have done if I wasn't, if split didn't exist, I would need an array list of array list because I don't know the dimensions beforehand. But I can use a string because split will give me the correct number of items and I don't have to know what the count is. And that is why we have an array list of an array of string. So the array list carries our rows and the array of individual letters contains our columns. And in the book, I say this is what's called an ad hoc solution, which means I just did it because that seemed like the best way to do it. Gosh, I'm just not sure if, again, even when I was doing it, I wasn't sure that this was the right way to do it. But then somebody once told me the first way that you think of that works is the right way to do it. And this will work. So we're going to stay with that. You may want to rewrite it into an array list of array list. If you really want to, you can do it. But again, this may not be moral, but it certainly is expedient. Now, these things here we're going to need to use for the turtle. Okay, it's turtle graphics. And here's our maze where we're going to give a maze file name. We're going to create a file. And notice we've got try with resources here. I'm bringing in an input scanner, which is going to be a new scanner based on the input file. And that comes before the opening brace of the try clause. So now we're going into Java. Okay, we're through with the recursion part of our thinking for right now. Now we're talking about all the weird stuff that Java has in it. I'm going to create my maze list, which is the array list of strings. And then as long as I have a line, I'm going to read it. I'm going to see where the starting column is. I remember I'm looking for the letter S. So I'm going to use index of to find the letter S in the string. If I have an S in the string, then that means I know what my start row is and I know what my column is because I'm keeping track of my row and the index of is giving me my start column. Then I'm going to add the result of splitting the string, which will give me my list of pluses and spaces. I don't have to do another loop inside of that. Finally, I want to know how many rows there are. And presuming that all of the rows in the maze are going to have the same length, they'd better, otherwise it would be a pretty weird maze. I'll just find out how long the first string is in that first string array in the array list is, and that'll tell me how many columns there are. Now, this is fun. Remember when we did the turtle the last time? We had the turtle where if you move forward one, it moved forward 1 pixel. What we want to do is we want to build a coordinate system where every step to the left is 1 square, not 1 pixel, but 1 whole square. And every move that's up or down is a different distance. And that's what we can do here. When we have this habitat, we're going to create a new world that's 600 by 600 with a white background. And what we're going to do is this sets up the coordinate system. So essentially, here's my biggest negative number. I'm going to take the number of columns in the maze minus 1, divide by 2, and subtract a half. So instead of having the coordinate system be from 0 to negative 300 to positive 300, it's going to scale it so that it's exactly the number of squares that I have, the number of columns I have. And similarly here, I'm going to set my maximum negative coordinate and maximum positive coordinate on the y-axis. Then every time I say move forward 1, it won't move 1 pixel. It'll move 1 distance of the square that will get me to the center of the next place I'm going. This is all sort of weird, but that's one of the nice things. And this is, I'm not sure where one would study this. If you do computer graphics, you're going to have to learn about this. How to do transforming coordinate systems. If you've ever had, I'm going to put in a plug for this because I like it so much. Anybody ever heard of SVG? It's called Scalable Vector Graphics. And this is something where you can have something, for example, it looks like HTML. So I can have a line where x equals 10, x1 equals 10, y1 equals 10, and x2 equals 40, y2 equals. And you have a text file with all of that, and you give that to an SVG processor, and it'll draw a line from those coordinates. And it turns out that you need to know, if you're going to ever do stuff with computer graphics and vector graphics, you're going to have to know about this transformation stuff. So that's what we did here. And then, of course, I need a catch, because remember, when you open a scanner from a file, that's a checked exception. And here we are when we draw the maze. We're not going to do any updating until we're done. And the reason we're going to do that is because that will not only, that way we won't update the turtle every time we draw a line. Yeah, otherwise it would take forever. So if you stop the updating, all the drawing gets done in the background without having to be transferred to the screen. And a doubly nested loop where I draw a centered box. And I use the X and Y translate, and then in whatever color it is that I need. And then once I'm done drawing all of those, I set updating to true. And what that does is says, okay, now that all this stuff that you drew in the background, just take it and transfer it all at once. So the drawing happens in memory, so to speak, rather than on the screen. And when I'm done, I just dump it all to the screen all at once. And I'm also going to set the delay for the turtle to 0.04. Here, notice I set it to 0 so it would go as fast as possible. Now I'm setting the delay to 0.04 so we can see things happening and it won't be too fast. Drawing a centered box. Okay, there's not much to it here. Bring the pen up. Set the heading. Draw the 4 sides. And notice I say forward 1. I don't have to figure out how many pixels it is because the coordinate system has that baked into it already. If I do want to update the position, then I have to say, okay, let's get the row and column, and that'll be my value. If it's part of our path, then we're going to go to bright green. If we have an obstacle, remember there's going to be a string, and we have these constants defined. So I don't have to use plus and minus. Okay. If we've already tried it, then that's going to be a black dot. And if it's a dead end, we're going to color it red. And then we'll drop a breadcrumb. I don't know where that is. Oh, there it is, where I draw a dot in the current color. And then if I want to move the turtle to a specific place, and the reason I have this there is because I have to have this 0.5 so that I end up in the center of the square instead of at the corner of the square. So that's what the +5. 0.05 does for me. Finally, I need to know if I am at an exit. So if I'm given, if my position in the maze, if the row is 0, or I'm essentially, am I at an exit? Yes, I'm at an exit if I'm gonna go off the left side of the maze, the right side, the top, or the bottom. Otherwise, I haven't reached the edge yet, and it's not an exit. And finally, we have our search from. So I'm going to update the position, and then I'm going to see what my value is. If I have an obstacle, then no, I can't search any further from here. If I've already tried it, or I'm at a dead end, also can't do anything. If I'm in an exit, then I can update my position, and finally I have found a return. Otherwise, and this is, do you all know about logical short circuiting? Okay, they may have talked about this in the first class. Good, this is an important concept. So this is, I'm glad we did this. Let's say I have something like this. If n greater than 0 and count divided by n greater than 10. See me, I should do it in, sorry, I should do it here in Genie. Okay, so let's say I have I want to find the area. Okay, I guess I should explain what I'm doing here, shouldn't I? And this is not going to be a full program. Okay. Given a total amount of items sold and a number of customers, see if the average items per customer is greater than 10. If so, we had good sales. Otherwise, we had bad sales. So I somewhere in my program, we're going to have something like this. If n is greater than 0, because if I have 0 customers, that's not good. And the total divided by n is greater than 10. Now, what happens if n is 5? And let's say I have my total is 200 and my n is 7. Yeah. Is n greater than 0? Yes, it is. Cool. Is 200 divided by 7 greater than 10? Yes, it is. So we had good sales. Now, what happens if somebody accidentally enters a 0 for the number of people instead of some other, they wanted a 9, but their finger slipped and they put in a 0. It turns out that this is going to still work out fine. Okay. Is n greater than 0? No, it is not. Well, in fact, I need to write this. Okay, so. Now, you'd expect this to get a division by 0 error, wouldn't you? Yeah, because n is 0, and when we try to divide total divided by 0, we should get an error. And let's see what happens. Hey, it didn't blow out. How weird is that? And here's what's happening. Remember how AND works. when I have, this is what, so if A is false, B is false, the result is false. If A is false and B is true, false. If A is true and B is false, then false. If A is true, B is true. Yeah. If I find out that A is false, do I even care what B is? I already know that moment A comes out false, I know the result. I don't even have to look at B. It's in fact, it's a waste of my time to do that. That's called short circuiting, and that's what Java does. Java sees n is zero. Is zero greater than zero? No, it isn't. Okay, fine. This whole condition has failed. It never even has to look at this other part. It doesn't even have to try it, and it skips it entirely. And that's why we didn't get a division by zero error. If I had reversed the order in which I did this, if I said total divided by n greater than 10 and n greater than 0, now I'm going to have a problem because it's going to try and do the first one. Oh, unclosed comment. Okay. Great. Excuse me here. And now I did the division by 0. So in this case, the order in which you do the operations really matters. Yeah. But that's what's called short circuiting. As soon as Java knows the answer, it doesn't have to go any further. Similarly with OR. So here I have A, B, and A or B. I have false or false is false, false or true is true, true or false is true, and true or true is true. Again, the moment the first one comes out to be true, I don't care what the second condition is. I know I've got the answer already. And that's what's happening here in the maze. Well, it was a long way to go for this, but it was worth it. Have I found a path out to the edge of it, to the exit of the maze? Okay. If starting to the north, one row up in this column, if that search from comes back true, I don't care about all the rest of them. If it comes back false, then I have to go to this second condition and see if I can find an exit starting to the south, one row down from where I am. If that comes back true, I don't care about the rest. I don't have to do any more searching. I can get out immediately. But if it comes back false, then I have to go to the east. I'm sorry, to the west. I've got to go to the west, namely one column off to my left. If that comes back true, I'm done. I don't have to go any further. So this short circuit lets me do this rather than having a whole bunch of if, else, if, else, if, else, if business. It's very nice to know that this happens. And then finally, if I found it, then it must be part of the path. Otherwise, I'll update the position saying, no, this is a dead end. And then I return found. And then here I say, search for an exit starting at the current row and column. And lovely. It turns out that I do not have my files here. Okay, I'm going to pause the recording here for a moment while I move the files. Okay, that's much better. It compiled, and let's try executing this. Okay. I have the wrong, okay, the turtle has changed since this. Let me see if I can find the correct versions here. I hate it when this happens. Yes. Let's try it from here. There we go. So the black dots means it's already tried that, and those are dead ends because they're red. Now, depending on which directions we chose, we did north, south, west, and east. If we did north, east, south, west, we'd probably get a different set of paths that would be examined. So this thing is really examining a whole bunch of stuff. Yay, finally I found it. And then as it unwraps the recursions, it shows us the path that exits out of the maze. So that's that. And again, the weird part about this, I don't know if it's weird, but the thing to notice is that our recursion here is like only 5 lines. This is everything else was setting it up in preparation to do these 5 lines. And this is the way things typically, I think, work in programs. The actual core of it is not that much. It's all the error checking, it's all the setup, it's all the validation, all that stuff takes a heck of a lot of buildup. Professor, is that what you found when you have done stuff?
Yes, for sure. Yes, yes. The magic happens there. But the magic doesn't happen unless you have everything else set up correctly. Exactly.
Yeah. And that you have no idea. Well, in fact, we just saw that when I had the wrong version of the turtle and the world program. Okay. And don't worry, I will when I upload it today, I'll upload the correct ones. That's pretty much all I wanted to talk about with recursion at this point. Let's move on to the higher order functions. And this is something that is not directly related to recursion, but it works very well with recursion. Although the example I'm going to give, I'm not going to put recursion in on top of it because that would make 2 things we'd have to keep track of conceptually. So I want to just do each concept individually. Let's take a look here at let's do. Okay, so here I've got several methods for iterating through an array list of integer, and I want to create a new array list that has only the even numbers. Then I'm going to go through again and find only the negative numbers, and then I'm going to find only the 2-digit numbers. So here's my first one. It's called keep even. I give it an array list of data, and here's my result. And so I'm going to go through this with a enhanced for loop. If the item is even, I'm going to add it to the result. And then I return it. Okay. Keeping the negative items from an array list. Okay. Same thing here. Go through for each item. If it's less than 0, I add it. Keeping the 2-digit numbers. Okay. I've got this loop here. But this time in the loop, I say I have to check to see if the absolute value is greater than 9 and less than 100. Because I want negative 37 is a 2-digit number. It's negative, but it's still 2 digits, right? And that's why I need the absolute value. And I'm going to return that. And there's absolutely nothing new here. We've done this sort of thing oodles of times. And here's my main method where I have a list of numbers. And I make it an array list by using arrays.asList. Sort of cheating there, but it's easier than having a whole bunch of add calls. And here are my evens. I call keep even. Here are my negative number elements and my 2-digit numbers. And you know what? I need to add something here. Otherwise, it's really hard to tell what the results mean. So there's my original one. Those are the even elements. Have 2 negative ones. And yeah. Any questions on that one? Well, this is all very nice, well and good, but boy, that's a lot of repetition. This loop here is the same for everything. The only thing that's really changing here is the body of the loop. Wouldn't it be nice if I could do something like this? Have a generalized method called keep. You give it a list of data and you give it a Boolean method that will give you back a true or false. Gee, wouldn't it be nice if I could pass a method as an argument to another method? Yeah. So I'm going to go for each item in my data. I'm going to say, if that method that you gave me returns a true, I want to keep it. Otherwise, I won't do anything. Then here in the main method, what I would say is, okay, I'm going to have an array list of the evens. I'm going to keep from the numbers list. And here's the method I want you to use to figure out whether you keep it or not. This is a pretty neat idea if you think about it. And then for the negative numbers, I'm going to use keep. I'll pass the numbers, and I'm also going to pass this method. So every time you get an item, you're going to call this method, and it'll give you back a true or false to tell you whether you want to keep it or not. And this is what's called a higher order function. A higher order function means it's the ability to pass a method to another method as a parameter. That's also possible, by the way, to return a method from a method. So you can actually have them. So essentially, methods are first-class objects. They work just like any other objects. You can pass them in as parameters. You can return them from a method call. And this gives you a lot of flexibility. Now, my loop here is only once. And the code is the only thing that changes. So again, wouldn't it be nice if I could do something like that? And the answer is yes, it would be very nice. And in fact, we can do this. Unfortunately, it's not quite as straightforward as this conceptual model here. So let's look at the functional keep items. What we're going to do is we're going to have to import something called a predicate. A predicate, I may as well put this in a comment here. Predicate is a function, and I'm going to use the word function here because this is part of what's called functional programming. We can, in this case, function and method are interchangeable. Function with one parameter that returns a Boolean value. So what I'm going to do is I'm going to have my array list of whatever type I have. It's going to be called keep. I'm going to give it the data, same as we did before, but this time I'm going to say, I'm going to give you a method. I'm going to give you a function that's a predicate. So you are going to be expecting to get a method that takes one parameter and gives back a true or false. I'm going to create my empty list for the result. And then for each item in the original data, I'm going to call the test method of the predicate. So that will do the body of the predicate. It's the same thing that I was doing here, the Boolean method of item, okay? But I can't just give the method name. I have to say, take that predicate I gave you and do the test method. And if it comes back true, add that item to the result. Here, our main starts off exactly the way it did before. And I guess I'll add the and this time I'm going to call keep. I'm going to give it the numbers, which is my array list. And here is my predicate. My predicate, it looks a lot like a method call, doesn't it? Except instead of having, it puts this arrow in here. There's no, okay, let's pop this out here. If we were doing this as a totally independent method, we'd call it Boolean, let's say, is even, and we'd have an integer n, and then we'd return n mod. So to make a predicate, what we do is we get rid of the return type, because predicates always return Boolean. That goes away. We get rid of the name. And then all we need to do is put the parameter list and an arrow, and then the body of the method. This is what's called an anonymous function. Because history. There's a whole story behind that, and I'm not going to go into it right now. Yeah. And then I'll print the evens. Now, this gets a little bit tricky with all of these braces and parentheses and arrows. And people say, yeah, I don't know if I can keep track of that, especially when I have these parentheses out here and it gets a little bit messy. You can also create a predicate independently. So for the negative elements here, I'm going to create a predicate called is negative, and it's going to have the parameters, the arrow, and the body. And then I'll keep numbers and I'll give the predicate to use. Again, I could have done it as an anonymous lambda. That's perfectly okay. But if you don't like using these anonymous functions, you can make it explicit and give the predicate a name, which I've done here and also here. And compile it, run it, and it does exactly the same thing, but there's a lot less duplication. Because all of this stuff here is going to work regardless of what the predicate is. I just pass in the test for whether I want to keep things or not. This is an incredibly powerful thing, especially when things get more complicated. If this method here had a lot more stuff to do, I wouldn't want to duplicate it over and over again. So the ability to say, okay, here's the outline of what to do, and I will give you a method to work with. And now it turns out, by the way, this has been in Java for about 10 years, and I did not know about it until last year. When I found out what Java actually has this is absolutely cool. And the reason is it's just, I'm not sure why it's not taught. Probably because it's a semi-advanced concept, but y'all are good with advanced concepts, so I'm not going to worry about this. Now, on Wednesday, what I'm going to do is I'll go over this example again. And remember the Newton's method that we did either last time or the time before last? Yeah. And we did square roots, right? Well, gee, what if we wanted to have a generalized method that would find the roots of not just square root equations, but cube roots or polynomials, okay? Without having to write the recursive part of it, the part that actually does the comparisons over and over and over again. This is a perfect place to use these anonymous functions. We can say, okay, find the root, and here's the function I want you to find the root of, and pass that on to the method. I think this is incredibly exciting stuff. Everybody's like, what the hell is so exciting about it? Well, find out on Wednesday, okay? And that should do it for today, unless there are any questions from out there. Let me check to see if there's anything in the chat. Nope. Okay, then I guess I'm going to stop sharing here and stop the recording. Professor, do you have anything else that you want to add?
No, just enjoy the eclipse. That's it.
Okay, thanks. Will do.
All right. Thank you.
You're welcome.